our next invited speaker, both of them come from the Spanish National Research Council. I'm joined here by Álvaro and Judith, and they're going to be giving a talk on the use of Flower and more broadly federated learning within the area of the European Open Science Cloud, where there's a variety of applications and scenarios that are all very important. And one of the ones that caught my attention, because I haven't seen so many applications of its type, was in the direction of water quality. And so I'll hand over to Álvaro and Judith to tell us all about it. But I really love the idea of federated learning and in particular Flower being used to develop these applications that assist how we can care for the environment better. So over to Álvaro.
Hello, everybody. I hope you can see my screen. So,
yeah.
and that you can hear me okay.
Yeah.
So, thank you, Nick, for inviting us to this event. We would like to present here how we are dealing with federated learning in the context of the European Open Science Cloud, explaining a little bit of introduction of what this EOSC, European Open Science Cloud is, and then I will pass the floor to Judith so that she can explain the specific use case you just mentioned. So first of all, I would like to briefly present in 2 or 3 slides what is this European Open Science Cloud, because this is where the context of our work is. So these slides are not from me; these are from the EOS Focus European project that is coordinating and supporting all the actions within the European Open Science Cloud. The vision of the EOS. This is an initiative that is being created by the European Commission and the European Union in order to create what they call the European web of fair data and services for research. By fair data, we mean here research data that is easy to find, access, interoperate, and reuse. This is what stands for fair: findable, accessible, interoperable, and reusable data. In order to make the research outputs available for all scientific disciplines and for all researchers in Europe and beyond. Why? Because there is a lot of potential that has not yet been unlocked in Europe. This is the statement from the association and the Commission. Who is this European Open Science Cloud? This is open for researchers and innovators that are willing to follow the open science principles. What it is not a single cloud infrastructure. The word cloud here is a bit convoluted. It is a system of systems that will allow researchers to join other infrastructures, other services, bring data together, and provide added value on those data, always with this open science paradigm in mind. This is the framework where our project is being developed. And let me introduce in a nutshell what is our project. Our project is called AI for EOS, which stands for Artificial Intelligence for the European Open Science Cloud. It is a research and innovation action from the European Commission that is trying to build a platform for distributed, federated, composite learning AI in this context of the European Open Science Cloud. We are 7 academic partners, some small enterprises, 1 non-profit organization. Our objectives, I will summarize very briefly here, as I already introduced, are to provide these feature-rich services in the EOS focusing on the development of AI applications, support for building AI systems on distributed datasets, and here is where federated learning makes a point in our proposal, to provide developers with services to compose AI modules, enabling more complex data-driven AI applications, Our fourth objective is to create an exchange of open AI models that are focused on science and exploiting resources of European infrastructures, with the final goal of extending the service offer of the European Open Science Cloud with a focus on AI, machine learning developers and data scientists. We come from a previous set of initiatives where we started to exploit this idea. We developed some years ago the Deep Hybrid Data Cloud project that provided access to European researchers, transparent access to accelerators that were already available in the distributed pan-European clouds that exist, like the EGI Federated Cloud, for example, and beyond. And we are now evolving this software in order to provide this set of advanced features where we think that federated learning is one of the central points for the next years. This is our very high-level architecture. We are leveraging mostly open source components that are being integrated in order to create what we call the AI for EOS platform. At the bottom, we have resources coming from cloud infrastructures provided by commercial providers or by open source projects like OpenStack. We are federating all of them in a platform like using HashiCorp Nomad. And on top of this HashiCorp Nomad, we are deploying Flower in order to provide scientists with this access to federated learning systems easily. In order to do so, we are developing obviously some tools like our own API and the dashboard that will be demonstrated by Judith later on. These are our features regarding the platform. We have completed the first year of the project in September this year. We are already providing a federated learning server for our users, and we are working towards the integration with different authentication and authorization modules that will extend Flower to provide fine-grained access to the resources. This is how our federated learning scenario looks like. We are providing the users of the AI for EOS platform with this collaborative and decentralized approach to build machine learning models by exploiting Flower. This has been the tool of our choice due to the simplicity of the implementation and the easiness of the deployment. It is not convoluted, it goes straight to the point, and it fits perfectly in our architecture. We are providing users with the ability to manage the experiments through the dashboard, and we allow users to participate within the platform so that different trainings can be executed on top of our resources or externally, which is the most important scenario for federated learning. So everybody can join an experiment with authentication in order to contribute to the training of the overall model. Some common features that are related with this: we are working on implementing authentication modules for Flower. We are working right now with bidder tokens. We are extending it to use some secret management systems like HashiCorp Vault. Profiting from the architecture design that we have done for Flower, we are also working in other distributed training schemes like split learning or parallel training with Horobot or the TensorFlow parameter server. And we are working towards more updated features for this, the training of the experiments. This is all from my side as an introduction. So I will open the floor to Judith, that will continue with the specific use case of our project and how we are implementing the federated learning in the project. So Judith, the floor is yours.
Thank you very much, Álvaro, and thank you, Nick, and all your team for inviting us today. I'm going to share my screen, so now you should be able to see my screen.
Yes, looks good.
Okay, so well, I'm going to start by talking a little bit about federated learning and how have we used Flower in the AI for Use project for performing a federated learning training. So here we have a screenshot of the dashboard of the AI for Use platform in which we can see different models. So for example, if we see here the image classifier, this is a model that we can deploy in order to train an image classifier with our own dataset, but it comes pre-trained using ImageNet. We can create different models or from scratch, we can create our own deployments, but we also have these tools here in which we can find the federated learning server, which has been created using Flower. So if we go to the configuration of this federated learning server within the platform, within this dashboard, we can see some general configuration regarding the password that we will need to use to access to the interface, the name of the deployment, and so on. Some configuration regarding the hardware configuration, and the most important part in this case is the federated configuration, in which the user just needs to include the number of rounds for training the federated learning schema, the minimal number of clients that will be needed for starting the federated learning training, the evaluation metric that will be used. In this case, as an example, we have included here the accuracy, but we can even include more than one metric. For example, in some cases, we may need to use the mean square error together with the mean absolute error. So we can include more than one. And then last but not least, we have the federated aggregation strategy. Here we have 5 predefined aggregation strategy that are implemented in Flower. So this is the quite simple interface that the user will see before submitting the module. So when we submit this federated learning server, we will have a quite intuitive interface in which we have this README here, in which we can see how we launch this federated learning server, which is quite simple. In this case, we just need to run Python 3 server.py because we don't need to do these steps here because we have used the dashboard. And how can we get started? So if we go to the code of server.py, in which we have the Flower server, we can see that here we are reading the variables that has been introduced by the user, the number of rounds, the metrics, the number of minimal clients, and the strategy introduced. And then we can just have here the Flower server in which we started, and then the different clients can connect to it. In order to connect with the server, the clients that, as Álvaro has already mentioned, can be deployed, for example, locally in our own computers, but also in external cloud providers, or even in another AI for Use deployment. They just need to introduce the deployment ID in which we have deployed the federated learning server. This is explained here in the getting started. We can see that each client of the schema must enter the endpoint following this schema here, and then the clients will be connecting to the server. So then the users just need to run this file, this server, and then start the different clients and connect them to the server. So let's take a look with a first client in which we just run the code in which we have the client. So following the Flower guidelines, we have created a class called client number 1, for example, in which we have introduced the different functions for training this federated client and using the NumPy client of the Flower library. So we just connect here this first client. We can see the connection is ready. This from the client side, and from the server side, which will be deployed in the A4S platform, we will receive this message, which we are all used to, but the federated learning process is starting. So now, if we introduce the second client, we will be able to see from the A4Use part, we will see this from the server side, the evolution of the process in which the federated learning is starting, and it starts when it receives 2 clients out of 4. So then we have the first round with 0 failures, we can evaluate, and so on. So this is how we can perform a federated training in just 1 minute, let's say. using the A4S platform in a quite intuitive way for the user, because we are using the interface that I have shown you previously, in which we just need to write, okay, I want this metric, I want this number of clients and this number of rounds. So it's quite easy for the user to deploy the server and then to connect the different clients to that server. So that's how we can start a federated learning in the platform. Now I'm going to move to this specific use case that we want to talk about, which is already presented in this paper here. Is about environmental sciences, but about water quality in particular. So first, let's start by mentioning that, as we all know, fresh water is an essential resource for life, and we need to maintain it properly. So it's quite important to focus in techniques such as monitoring, which can help us to do so. So in this case, we are going to focus on monitoring the concentration of some pigments that we can find in some water bodies, like chlorophyll. In this case, this is a key task to contribute to water conservation, to the water bodies conservation. Nowadays, with the existing sensor technology that we have, it's quite difficult to have measures in real time with enough frequency in order to be sure that we are properly assessing the risk management of this kind of blooms that can arise due to a lot of amount of concentration of chlorophyll. So in order to avoid these kind of problems, we can use deep learning models, and in this work we are also using federated learning, not only deep learning. So in this case, for this data-driven application using deep learning, we are going to use 3 hydrophysical features and 3 meteorological features in order to be able to estimate the concentration of chlorophyll in 2 rivers, in 2 tributaries of River Thames. So we are going to use 3 learning paradigms. We are going to compare the 3 approaches that normally and naturally arise in this case, which are individual learning, centralized learning, and federated learning. In this case, we have 2 rivers. The first one is Emborne, which is a rural environment, and the second one is the river Dicat, which comes from a urbanized catchment. So there are quite different conditions. The rivers have quite different conditions because of their area. So let's take a look to the data processing that we have carried out and the features that we have analyzed and that we are using in our deep learning model. First, it's important to highlight that all the data that we have used in this study are openly available. First, we have data containing information about the 2 rivers, River Emborne and River Dicat, which are obtained from the Environmental Information Data Center of the Center of Ecology and Hydrology, belonging to the United Kingdom's Natural Environment Research Council. And we have selected just 3 hydrophysical features, which are the water temperature, the pH, and the electrical conductivity. There were a lot of features in this database. There are others such as the oxygen dissolved and the flow and other features which are also quite important for water quality monitoring. But in this case, we have decided to only use these 3 because are the easiest to collect, and the sensor that collect them are the most common ones and the easiest ones. So it's quite common to have these features in other future use cases. So that's why we decide to use these 3. In addition, we think about introducing other features that are openly available that could help to improve the study. So we decide to use meteorological variables, such as the global irradiance, the air temperature at 2 meters above the ground, and the one displayed at 10 meters above the ground. Then we need to detect and to remove some outliers that arise in these cases. So in order to do so, we use the growth rate and the Takis test. We can see here in this time series how can we detect the different outliers and remove them. We have used the growth rate in order to not remove values that could seem anomalous but are not outliers, because we can have some natural phenomena that cause some peaks, for example, this or this, but may not be outliers. So we take special attention to that. Here we have the features that we have analyzed, comparing their values and their distribution in the cases of Emborne and the cases of Dicat for the train split and for the test split. You can see that there are features that are quite different. For example, the electrical conductivity, the distribution in the two rivers are quite different, and there are others that are more similar, such as the temperature and, of course, the three meteorological ones, which are almost the same distribution. So I talked previously about the three approaches that we are going to use in this study. First, the individual learning. I think that is the most intuitive one we can think about because we have two rivers. So let's train two models. The same model for the two rivers, just in order to be able to compare the results of the three approaches, but two models, first for the river the Cat and the other for the river Emborne. Then we evaluate them individually in each river and train each model during 500 epochs. In the case of decentralized learning, I think that it's also quite intuitive to apply this approach because we have two rivers that are quite different according to their natural state, because one is more rural and the other is a urban one. But it's interesting to try to centralize all the data together and try to train the model and see how good is the generalization ability of such model. So we do that. So it's partition for both river with were joined together, and then we test individually in each river. So we train during 500 epochs again. And last, we have federated learning. Here it's clear that we have two potential clients, which are each of the two rivers that we have. So we consider three cases here. First, training during 10 epochs, then during 50 epochs, and finally during 100 epochs. Associated with the number of epochs, we associate a maximum number of rounds of the federated learning schema in order to be able to compare the three approaches properly. So, in the case of 10 epochs, we train the model a maximum of 15 rounds, and so on, as you can see here. Then we optimize the number of rounds of the schema according to the mean square error that we obtain both from the train and the validation set that we have for the two different rivers individually. And we can see here in these two tables the results that we get. We could expect that the best results will be obtained for the individual approach because the two rivers were quite different. But here we can see that in the case of the Cat, the best results for train were obtained with the federated learning approach, not for test, but are more balanced, let's say, because here the error for train with the individual approach is bigger than the one obtained with the federated learning, and we are reducing a little bit the error for test. Same happens here. We can see that we get a slow error for train with the individual approach, but the error for test is better with the federated learning one. So it's quite difficult to find a balance between train and test because of the condition of the river. There was special issues in the test which were quite difficult to predict just seeing the train, but we can see the potential of the federated learning application. And in the same line, in the second table, we have the results obtained with the 6 features, because we tested first only using the 3 hydrophysical features, and then we introduced the 3 meteorological ones in order to see if we can see some improvements. I think that we are going to see it better by taking a look to the time series and the predictions that we get. Here we have the prediction for Emborne for the test set. We have in green the observed values, and in purple we have the predicted one with federated learning. We can see that we can capture this first peak here well with the federated learning approach. It's a little bit better with the individual one, but not with the centralized approach. And same happens here, in which we can see that the individual and the federated learning are quite similar, but the centralized one is quite worse. And same happens in the intermediate parts of the time series in which we don't have peaks. And here for the Cat, we have again that this first peak is well captured by all the 3 approaches. In this case, we have in blue the federated learning approach for the Cat. This other peak is also well captured by the federated and individual approaches, but not for the centralized, which performs worse here. And this other peak is only well captured by the individual approach because it's quite anomalous. We have taken a look to the features that we had in that moment, and it's a quite anomalous value. So that's why even the individual model is not taking it so well. In this case, these models have been trained with data capture each hour. But what happens if we have less number of data? For example, if data is just captured each 24 hours or even each 1 week, we just take one data each week. It can be, we can think that this is quite anomalous, but it's not, because in some cases there is one person who goes to the water body and takes the measure from the sensor. So it's quite common to have a lower amount of data. So we decide to test what happened in these data reduction scenarios. We are simulating that we have less data for training in order to see what happened in these cases. Because if we think about the individual approach with a lower amount of data, we will not probably use it, and we will think, okay, I have a lower amount of data, maybe I will need to centralize it. What we have seen is that in these cases, the federated learning is better than the centralized approach in a lot of scenarios, because I have just shown these two. In the paper, we show 3 cases. And we can see, for example, here in each 24 hours, that the federated learning approach is capturing quite well this peak here, not the centralized one. And here, all the 3 approaches are capturing this peak. In this other case of the cat, this first peak is well captured by the 3, a little bit better for the federated one. And again, this anomalous peak is not captured by none of the approaches. And this one is just captured by the federated learning approach. So, in order to conclude, with this study, we have seen that the machine learning and deep learning techniques can be quite useful for predicting the chlorophyll concentration using only hydrophysical features, but also when we add the meteorological ones. As we could expect, when we have a lot of data, the individual learning normally provides better results for training. But when we combine the information from the 2 rivers, which are quite different information, quite different values for the different features, the federated learning paradigms can result in a higher generalization ability, which can be seen for Enborn especially and for the test split of such river. Also, just to conclude, these results show that the federated learning approach has quite interesting applicability, especially compared with the centralized one, especially when we focus on cases when privacy or technical conditions require to use these kind of approaches. For example, when we have a low amount of data and we cannot use the individual approach, when we have little data available, or when we have privacy issues that do not allow us to centralize the data altogether in the same place. So if you want to check the full paper in detail, we have included here the link and the code that you can scan it and check it and take a look to the work. So that's all for my side. So if you have any question, comment, thank you very much.
Thank you for the wonderful talk. It's really an interesting platform and series of applications that we just heard about. I've gathered up a few questions as you were going on that people asked, but I noticed that Javier had a couple he wanted to ask himself. So over to Javier first.
Yes. Thank you, Nick. Yes, thank you, Judith and Álvaro. I think this was a really interesting use case for FL. And I have, I think 3 questions, but I'll start with 2, just in case somebody else wants to ask something. For the hydrophysical and meteorological features you were describing, Judith, so you had 2 clients because you have 2 rivers, but I was wondering if the data is gathered at different points along the river, and if that's the case, would it make sense to have one client for each, place where the data is collected, where the chlorophyll is measured, maybe? And in this case, do you think it will work better?
In this case, all the data, for example, for Enborn, there were only 1 point of capturing the data, so there's no problem for that part, and the same for the cat. So we have only two clients for that reason, yeah. And we have been working in another work in which we have a different water body. It was not a river, and there were points of measuring in different places, but we have not already tested. And again, it happens that we need to test what happened first in the train split, in the test split, because the difference are huge. In this case, we have seen that even due to natural phenomena, there are quite different conditions for train and for test. So I cannot say if this will be working properly in other situations, because they are quite different.
Okay. Yeah, makes sense.
I think
If I
Álvaro
may-
wants to say something.
Yes, I just want to add a couple of things. As Judith said, for the river and the airborne, for this specific case, there were only two sampling places, let's say, two sampling points. So that's why we had only two clients. But the point with this kind of data sets is that they are not so easily findable. Also, when you go, for example, with some companies or with some research groups that are using the same data, it is difficult because it is really time consuming. I mean, in order to have a large data set, maybe you need a 5-year, 10-year campaign. So data sets are not so easily findable. We are now in the process of checking another data set that we have found, that we got access to, that contains information from rivers from France, that contains historical campaigns for much more sampling stations and much more with a larger time frame. So in this case, we will check, obviously, if considering each of the sampling stations as a client will make sense and will improve the predictions, but not for this specific case because we only had two sampling points, let's say.
Yeah, I think it will be quite interesting to see, if maybe having more sampling stations along the river could help mitigate the presence of one river is so different from the other because where it flows, for example. Okay, moving to my next question. Could you talk a bit about the type of model, like the type of architecture you use for this particular set of rivers? And do you think it is lightweight enough, for example, to run directly on the hardware that this sampling station might have, which might be very constrained, for example?
In this case, as we just wanted to compare the individual centralized and federated learning approaches and just have an idea of how is working each approach, we perform a quite simple convolutional neural network. I have here the number of layers, but I think that it was like 10 layers, something like that. So probably it could be running in different devices because it's not quite complicated. It's a quite simple model, but it's because our objective was not to create the best model for this objective, but the model that we can use to compare that works well both for Reborn and for the CAT, and that we can compare in the individual centralized and federated learning approaches in the same conditions, let's say.
Yeah, I think makes sense. Okay, cool. I think those were my two questions. Thank you very much.
Thank you very much.
Sorry, I just forgot to unmute. I had a couple of questions that came in. They came in two basic varieties. One was related to the platform, and the other was related to the actual application research we heard at the end. Just about the platform, it seems fascinating. I can kind of see what they're getting at. And so the tenor of the question is, can anyone use this platform, or is it only for scientists, or is it only for people in this research grant? Who can use it?
Well, the point now is that it is closed for the collaboration, basically because we are still developing it. But we are, the platform is developed and is ready to be used, but we are adding these new features. Therefore, we are for the moment only using it within our platform. So we have three different use cases apart from this one that we just showed that are officially driving the evolution of the platform, but we are planning the first release and open it to the public in, if I'm not mistaken, by the beginning of March. So we will have a fair release of the platform. We will open it through an open call for specific use cases. I mean, we cannot open it widely to the public, basically because of resources, not because of anything else, hardware resources. And then the point is that, I mean, the European Open Science Cloud is focused on supporting researchers and innovators, regardless of if they have a grant, if they have funding or not. But this is still the funding model and the access model within the EOSC is still being is something that is being developed. But for example, we have another deployment of the platform that was done in parallel with the EI4EOS platform, which is called the iMagine platform, which is done by a sister project that is tailoring our platform with our software for the exploitation of AI techniques to analyze images that are related with ocean and aquatic research. So there, for example, there are different use cases, around 10 use cases, if I'm not mistaken, exploiting underwater images, satellite images, webcams, and so on and so forth for very different use cases. And there are providers that provide resources for those use cases. So the point is, on the one hand, we have the platform that will be offered through the European Open Science Cloud for EU researchers and obviously related associated countries like Switzerland, UK, Turkey, and so on. And then we are also delivering the software so that somebody with enough resources can deploy their very own tailored platform for their needs.
I see. And so then this is it Image or Imagine a platform? You mentioned that they're doing something similar to that right now by using your software.
Yes.
I see. Great. How many scientists are using what you presented today right now?
The current setup, I would say it's been exploited by around 50 scientists that are, as I said, they are part of the use cases, part developers of the platform that are also doing data science, and some other, let's say, well, not use cases from the project, but since our institution, for example, CSIC, is really large, we are more than 120 institutes in Spain, we are gathering different users and offering the platform internally for them. Imagine, I think it will be also around 50 scientists at this moment using it for specific use cases. But obviously, when we open it through the European Open Science Cloud, we expect that the number explodes. The previous platform that we are building on, which was called the Deep platform, when we took the baton of the software and the platform deployment and so on, was serving around 100 scientists.
Well, I mean, 50 is a big beta trial, really, when you're trying to build a piece of software and understand how it's going to be used and so on. So that's quite impressive already. I guess the other type of questions that we received, if I just take a few of them, I guess. So this is with regards to the water quality study. One question that came in was, does this particular scenario expose some areas of federated learning research that need to be done? So I guess they're talking about some problems that would be more in the domain of how you do federated learning, where they're sort of new problems, or maybe some things that were very difficult that the scenario required, that then maybe some of the computer science, federated learning specific researchers might go away and try to solve?
Yeah, in this case, we decide to apply the federated learning to this kind of data, which do not present, obviously, any privacy restriction and so on, because maybe we can encounter different technical restrictions. And in order to test if we have some computing capability in the centers in which we are collecting the data, maybe we can perform this training without centralizing the data. And why are we interested in doing this without centralizing is just because we have tested that in some cases, as we have already saw, the federated learning approach performs better than the centralized one. And that was the reason to try to test if in this case it makes sense to apply federated learning. Maybe we could have encountered that the centralized approach works better for this case, but it wasn't. We find that the federated learning performs better in some cases, had better generalization ability in this specific use case. So that's quite interesting in order to be able to know that maybe if we have the computing capacity of the sensors, of the devices that we use in the different water bodies to collect the data, we could perform this kind of training as it is. An individual approach, which could be feasible if we have such computing resources, and we will avoid the problems of centralizing the data problems. I talk about problems of connectivity and so on. In some cases, as Álvaro has said, we need a lot of years of taking measures of the sensors in order to build a large data set. So that's why performing it federated could perform better, because we get more data, let's say, from different points, but more data.
I see. Interesting. Along the same lines, there was a question about, could you explain a result that would have not been possible without the federated learning? Maybe this could be a result, I suppose, that maybe you haven't got to yet, but within this water quality application, the fact that you're federating it as an approach, did that allow you to do something that you couldn't otherwise do? I guess that's kind of what they're getting at.
Here I have one answer that, well, I don't know if it is an answer or if it is a guess. But for example, in this area, at least in Spain, but I guess this is mostly worldwide, there is an important point in water treatment plants, because right now there will be a change in the EU directives for wastewater treatment plants, so that the values of some compounds will be much lower, and therefore there will be a need for the companies that are managing these plants to let's say monitor these values more closely. But there are no sensors to do so. Either the sensors do not exist and you have to grab the sample and go to the laboratory, or either the sensor is too expensive and too fragile, meaning that it requires a lot of maintenance, and if the maintenance is not done properly, it will give you weird values. So having a system that allows you to monitor these values, obviously using as a proxy some other variables like a machine learning system, this can give you an idea of how the whole system is performing, and then you can do the manual measures of those values by getting a sample and going to a lab. But this is feasible in theory, okay? But the problem that we have is data again. In order to train a model, you need a lot of data, and sometimes those data do not exist at all because those companies were not collecting it or were not monitoring it properly. Mm-hmm. And the second point is that, at least for example in Spain, we have a lot of companies managing different wastewater treatment plants in each region, in each county, in each city. And obviously, these are commercial companies, and they are not willing to share the data. If we could join all the data that these companies are gathering, and we could build a large data set, maybe we could apply a model. I mean, not for the whole country, because it is very complicated, different conditions, cities, and so on. But maybe for specific areas, we could build, let's say, a global model in order to make these inferences, or at least a robust model. But obviously, these companies are not willing to cooperate and give you the data, because these are their insights on the processes of these wastewater treatment plants. So if we could convince them to join a federated learning experiment by just providing, but not providing the data, but just joining the experiment so that we can build this global model, maybe we could tackle this problem that does not yet exist, but will exist in the near future, probably.
I can see. Yeah, I mean, I like the fact that this sort of parallels a lot of the discussions that we see in healthcare, for example, but in a completely new domain that I think is equally important.
Yes,
but you really
indeed. I mean,
sort of understudied.
In health, in the end, you have the data privacy from the, let's say, patient's perspective. Here, it is data. I mean, there is data privacy, but from the company perspective, that they don't want to give the individual samplings, because, for example, I don't know, you can get insights on how the wastewater treatment plant is doing one process or another. So there is a lot of parallelism here.
Final quick question would be, just are there any exciting other papers coming up in other domains? You mentioned that there are some other use cases. So I couldn't help but wonder if there is other type of research you wanted to kind of just mention being done already using this platform.
Judith, maybe you can comment on the agrometeorological case.
Yeah, we're working on applying federated learning to an agrometeorological case in which we have radar images capturing different. We are simulating different areas because we only have one radar, and we are splitting the radar images into areas covering different areas of a same country. So we want to apply this federated learning architecture to such data. And other paper that we published, I don't know if it was 1 year ago, I think, was covering the health field, in which we apply federated learning to a use case in which we have X-ray images in order to predict if a patient presents or not pneumonia. So in that case, we were simulating that we have different hospitals. And in the same line, that's another plan that we have for the future, but it's quite difficult to find data. We want to collaborate with different hospitals in our region in order to perform a federated learning training using medical data that they have regarding different topics, for example, cancer and other topics, and to perform such federated training with images, with medical images, capturing the different hospitals. Then we can encounter other problems in that field because of the machines that are used to capture the medical images and so on, but that are other issues. And I think that there are quite different fields in which we can apply this kind of learning approach. I'm going to mention one last one, which is inside the scope of the AI for Use project. We have an internal use case which is about thermography. So we are capturing images using drones in different cities of Germany. So the idea is to the future, when they have all the data captured, they are already developing the models. We want to perform the federated learning approach, in which one client will be regarding the images captured in one city, and the others clients will correspond to images captured in other cities. So that's other application that maybe we could be carrying out within the scope of this platform, of this project.
Wow, they sound really interesting scenario. That's really cool. Well, thank you so much, both of you, for presenting today and describing really impactful work. This is really exciting stuff. So thank you so much today.
Thank you very much.